Hello.
Yeah. Hello. I can start, right? Yeah.
Sir, can you stand little bit this side?
Yeah, sure. Yeah, you can raise the hand and they will, put it in the middle, somewhere in the middle. So you can raise the hand and they will hand over and then you ask. Okay. Good morning. So let us resume our discussion. So in the previous classes, we have seen how to detect the key points and how to extract features around the key points. We have also seen if we have an object, several key points describe an object, and the features around each of the key point essentially describe the object, different parts of the object. We have seen through bag of visual word kind of technique, bringing together those key points of a single object and recognizing the object using all the key points or essential key points or very frequently occurring key points of the objects. So the question now is, we have large samples, large number of samples images to be classified, recognized, and the key points are also in large in number. For performing any of the task like matching or saying that it is the same key point as that of the other key point and so on. So say if we consider a particular task like image recognition, say for example face recognition. So assume that we have the face images and we have extracted the key points around the face region. So you have a face image, okay, and then you have extracted some key points of this face region and you want to recognize across say large number of faces and large number of persons. So you have assume that we have 100 persons to be recognized. Say if I give a new test sample of a face, we want to put this new test sample to one of these 100 categories. Okay, that is the problem. So typically, as I mentioned before, many of the problems in computer vision can be tackled as a classification problem. So this is the classification problem which we now introduced. Say we have say 10,000 face images. Of say 100 persons, okay, and the problem is now to given a test image, these 10,000 face images of 100 persons are kind of labeled data, in the sense that, so we know out of these 10,000 how many belongs to first person, how many belongs to second person and so on, okay. So you can consider this as a kind of a label data or a training data. So when we have a training data or label data, what kind of classification technique can we use? Yeah. Since we are given a set of training samples, we can use supervised classification for classifying a test sample. So assume that I have 500 okay test samples, okay. So I have 500 test samples. Now the question is, given these 500 test samples, what I want to do is I want to put each of these them into these 100 categories, okay. So what is the name method that you know? Say each of this sample, so each sample is described by some key points, okay. Of course I can describe each sample by a key point, by a set of key points. So if I consider that there are some landmark points, okay, I just considered 4 landmark points, okay. So what I want to do is, in each of the images, I want to extract where these key points are, okay, and then a priori I will try to match these key points, saying that okay, at this location or for eyes I have got 2 key points and these are fine for eye, these describe eyes, okay, and nose one key point and some other key point somewhere, okay, something like that. This is one way of representing an image. That means an image can be represented by a set of key points. This is one way, or bag of visual words as well. That means we have already code vectors for face image, okay, face images of different persons, and we see the frequency of occurrence of the key points with respect to the code vectors. Okay, we have 5 code vectors, how many times, okay, these code vectors has occurred, or how many key points are associated to first code vector, second code vector, and so on. Okay, that is other way of representing. Or if we want to make a representation for a face image, directly I can bring in some kind of HOG vector for the whole image. If this image is say 50 cross 50 image, okay, so in pixel space it is 2500 cross 1 vector. Okay, if I just directly take the image intensities as the features, okay, so vector when we consider image intensities as features. Okay, within image intensities as features, whereas if I consider now representing this as a histogram of orientation gradients without going for key points, of course I can go for key points and then try to see whether key points match or not. Okay, usually matching the key points is very well encouraged for identifying the object across a bigger image, that is for a detection task, in the sense that say if I want to know where the face is in a big image, okay, I don't know whether the face is there or not, and if it is face is there, where it is in a bigger image. I have a big image here, okay, and in this image there are several objects, not just single object, okay, and then I want to know where a particular object is, okay. In such cases, or if I have a set of images, okay, I have one image like this and I have another image like this, okay. So there is a transformation between these two images as we discussed before, or there is a global or local motion of the objects in these two images, okay. How much each object has moved, I want to identify, okay. So for such tasks, especially for the detection task, the identifying or finding out the key points and using the key points is more encouraged, okay. But the task is directly a classification or a recognition, okay, then we can directly represent, say I know already a localized content, or we already localize the object, in the sense that face is here, okay, we are able to figure out where the location of face is. Now we just want a descriptor for the face, okay. In such case there is no need to go for key points as well. We can directly represent by different feature vectors which are rotation invariant, okay, photometric invariant or geometric invariant kind of features, okay. So we can go for a HOG representation of this. If we go directly for a HOG representation, so assume that I can bring in, since it is a image of 50 cross 50, one way is directly I can consider say some number of 18 bins, okay, or whatever the number of bins, and then I can get the for whole image I can form the HOG vector and get 18 cross 1, okay, HOG vector describing the whole image. That is one way. The other way is we divide this into grids, okay. So whatever 50 cross 50 I divide into say 10 10 10 10 like this, okay. So and then 10 cross 10 grids, okay. So if I divide this into 10 cross 10 grids or the different regions, small sub regions, then how many grids do I get? So I get 25 such things, okay. So for each of these 25 10 cross 10 grid, I can go for a HOG vector. If I bring in a HOG vector for each of the 10 cross 10, okay, for each 10 cross 10, if I bring in a 8 bin HOG vector, okay, what will be the total dimension of the HOG vector that describing the whole image now? For each 10 cross 10, I will have 8 bin HOG, okay. Then what will be the dimension of the HOG vector for the whole 50 cross 50 face image? 2000, oh sorry, how much? This is, we have actually 8 into 25, that is 200, yeah, 200 cross 1, okay, HOG vector again. This is usually preferred. The reason being, each of the local region has its own angular information or shape information, okay, because the shape information on the head or on the eyes, at the nose and different locations is different. That is being captured here, okay, in some sense. Since we already registered it, registered means we have identified in a bigger image where the face is, okay, and then we have put a bounding box to the face, okay. So we, in some sense, we put a bounding box such that the face is exactly fit in this bounding box, so that all faces will be say the eyes roughly are at same location, the nose roughly at same location in all the faces, okay. That is usually done. So if I want to perform a high level automated task, we start from taking the whole image, identifying or localizing the object, and then recognizing the object by first representing the object by a feature vector. After we represent the several objects, okay, of the same class and different classes which are of interest to us by feature vectors, then we go for a classification task, okay. This we discussed in the previous classes, initial classes, when we discussed about the either the whole pipeline of automation, okay, in computer vision. What did we said? We first start with pre-processing. Localization is also a kind of pre-processing here, okay. Of course, we can do segmentation in that previously when we discussed about fish classification. We said we need to segment the fish region or whatever, the object region, okay. So segmentation, detection, okay, or even illumination correction or enhancement, all these are pre-processing. Okay, so we start with pre-processing. Okay, and then feature extraction. This what we have discussed here is feature extraction. Okay, after feature extraction, we can, as I mentioned, it can be local features, global features, okay, or key point based features, okay, bag of visual word features, or any features, okay. So simple histogram also may work at sometimes. So red blood cells and white blood cells, if you want to classify, okay, just take, if you localize the red blood cell region and then the white blood cell region, okay, they with stain, red blood cells look red and white blood cells look blue, say with some stains, okay, then you can easily separate them by intensity profiles itself, okay. So sometimes they can be simple features, but sometimes you may need to have an elegant feature vector describing it. And pre-processing also, sometimes just denoising or enhancement, okay, histogram equalization, such things are fine. Sometimes you need to rotate it, or you need to align it, okay, or you need to localize the object, segment the object, all those things comes in pre-processing, okay, fine. Then comes after these things, we are with features of all the samples we would like to either classify or perform any computer vision task. Here we are considering of recognition. So a typical example of face recognition. Here it is classification essentially. Okay, what we are doing here is classification. Okay, so for classification, since we have some training samples, okay, we are started with some training samples, we are saying that we go for a supervised classification task. Okay. Okay, fine. So now we have 500 test samples. Okay, each of them, let's take the feature vector dimension as 200 cross 1. Okay, so each is 50 cross 50, and then you have feature vector dimension of 200 cross 1. Now each test sample has a feature vector of 200, even training samples, all of them have a feature vector of 200 cross 1. Now if I do not tell any classification methods, okay, what if I ask you to perform classification of each of these test samples to one of the 100 categories, okay, to which person it belongs to? Assume that a class has 100 students, okay, and I want to make the automated attendance I have taken all your faces registered somewhere. Okay, I have 10,000 face images. Okay, each of you, that means 100 face images per person, assume that. Okay, and then I have a test sample, 500 test samples. That means I have run 5 classes. Okay, in 5 classes I just want, or 6 classes, I have got 500 test samples. I want to see whose face, okay, each of the test sample belongs to. The overall attendance in that 6 classes I want to know. Okay, that is the problem. So how do we start? So let's take first test sample. I want to know to which person it belongs to. What should we do? We can simply find this is we would like to assign a label to each of the test samples. Problem is, okay, so how to assign? This is the problem. So now where do we start? Let's take the first test sample. Okay. So if we have the first test sample which is described by 200 cross 1 vector, okay, then what do we do with that? We take the Euclidean distance of all the what? Training samples, and then see which training sample is closest to that, nearest neighbor of that, okay, or closest to that, and to that, say if I see that, say take test sample. So test sample with say 200 cross 1 feature vector, okay, is compared with what? With all 10,000 samples. Okay. So if we want to do that, how much computational complexity we need? We have. So we have 10,000 samples. Okay. So we see the identify the nearest neighbor. So how many computations are needed for doing this? Say 1 test sample, fine, but it is of dimension 200 cross 1, okay, and then it has to be compared with all of them which are again 200 cross 1 dimension. So the number of computations, if we see for each comparison, how many number of computations are needed? For each comparison, roughly 200. Okay. So we can consider either correlation, normalized cross correlation, okay, because I have feature vector there, feature vector here, or we can consider Euclidean distance. Okay, either is fine. We have actually a number of computations are okay, 200 cross 1 into, so how many I have to compare? 10,000 samples. Okay, 10,000 samples, and then that's all, right. So this will then I have to find out the nearest neighbor. I have to sort them, in fact. Okay, after finding the distances of 10,000, I have to sort them again of order of 10,000 we assume. Okay, and we need to find out the nearest neighbor, minimum distance, or the maximum correlation, normalized cross correlation. So it's approximately of order of how much? 10 power 6. Okay, 10 power 6 operations we need to do for assigning a label, okay, or saying that this test sample belongs to a particular person, face of a particular person. I need these many computations. Okay, this is by what method? This is referred to nearest neighbor. This is referred to nearest neighbor classifier. Okay, this is nearest neighbor classifier. So for each test sample, just find the nearest neighbor. What do we mean? Why we are saying nearest neighbor? Because yeah, we are seeing essentially the Euclidean distance. If I have only 2 features x1, x2, okay, if the samples are like this, that means the training samples are all, I may know the labels of the training samples, but they are all around. Okay, and I have a test sample. Okay, now I want to put into one of the category. What do? I just see the nearest neighbor which is very close to this, and then assign the label of this to this. Okay, so I see the distance and then label of this goes to this. Okay, and finally what will happen for this? So you need this many computations. After doing that, after finding the nearest neighbor, assign what? Label of nearest neighbor to test sample. Okay, is this fine? This is what we do. Now the question is, if I want to do the same for all these 500 test samples or the second test sample, okay, will there be any reduction of number of operations because already I have processed so much? Okay, can I get the advantage of it? For second test sample, can I do lesser operations than this? No, we have to do the same thing again. So there is no learning happening as such. Okay, we are just trying to find out the nearest neighbor all the time. Okay, and X has to search over the whole samples, and whichever is the nearest neighbor we are assigning to it. Okay, so and as the dimensions and the number of samples increases, training samples increases, it is even more computationally intensive. And if you want to do for all 500 samples, the number of computations required are order of 10 power 8. Okay, 10 power 6 into 10 square here roughly. Okay, 10 power 8. And it is not in some sense proportional to the, it is not only dependent upon the number of test samples I want to test or classify. Okay, it is more dependent upon the number of training samples, feature vector, all those things. Okay, so it is not very welcome to do for the testing at large scale. Okay, and there is no learning happening. Okay, so this is a in some sense a basic approach for assigning a label to a test samples. And if you want to be more reliable, as I mentioned in the last class, we can go for 3 nearest neighbor classifier. What does it mean? Say I have all put these crosses, but assume that there are two class samples. Okay, I am putting some of them with circles. So the samples are like this. These circles are only this side, and then crosses are more this side. Okay, and I have now a test sample. Okay, the test sample is here. Okay, the test sample is here. Here is test sample. Okay, here is test sample. Fine. So now assume that I want to put it into one of the category. Okay, one of the category I want to put it into. To which category should I put? See, this will have smallest least distance, or nearest neighbor for this is this only. But still you see that many of the samples around that are from the other class. So if I categorize just based on the first nearest neighbor, I may go wrong. So what I do, in that case, what is better thing to do? Yeah, we take the yeah, of course you can take a radius around it and see how many nearest neighbors, okay, of class 1 and class 2 are there in that, and whichever dominates you can assign to that. Of course there is one method which does in some sense in that way, but other ways I can fix, because I don't know how many at each location. Okay, if I put a radius, whether will there be a nearest neighbor at all or not. Okay, so the other procedure of doing it is, I instead of looking at single nearest neighbor, I look for 3 nearest neighbors. Okay, so first nearest neighbor is this. Okay, and then second nearest neighbor is, okay, first one is this. Okay, second nearest neighbor is this, and then third nearest neighbor, let's put this. Okay, assume that this is the third nearest neighbor. Okay, so in that case it belongs to the say this is class 1 if I consider, and this is class 2, it belongs to class 2 now. Okay, first nearest neighbor says it belongs to class 1, but 3 nearest neighbor classifier says it belongs to class 2. 7 nearest neighbors classifier says again it belongs to 7 nearest neighbor. It says it belongs to class 2 because class 2 is more dominant here. Okay, so more the nearest neighbors I consider and take a decision to put a label for that a particular test sample, I will be more confident of. Okay, but if I keep increasing it, okay, I take 100 nearest neighbors, what do you think will happen? Or 101 nearest neighbors? Okay, I may go wrong. See, if the density of these samples is very high, okay, and then density of these samples is less, then what will happen if I go more and more nearest neighbors? I am crossing the closeness, proximity, then there is no question of nearest neighbor, or there is no meaning for the term nearest neighbor here. Okay, so usually what happens is, if I go from 1 nearest neighbor, 3 nearest neighbor, 7 nearest neighbor, usually the accuracy increases up to some extent and then they decreases. Okay, the reason being you are not, the method nearest neighbor classifier is assigning the same properties or the same label as that of neighbors to it. If you increase too many nearest neighbors, then they are not nearest neighbors. Okay, better not assign those labels to this. Okay, fine. So, but as we mentioned, there is no learning here. So, what is more welcome or what is required is to have a classifier which will learn from the training samples. Okay, and that information of learning, that knowledge of learning can be used very effectively for testing any number of test samples. Okay. So, one very elegant algorithm that has ability to learn from the data, mainly from the in supervised classification setting, okay, is neural networks classifier. Okay, we will see first, see the evolution of neural network classifier has started from of course motivated by the biological neuron, ability of biological neuron, wherein in our brain we have millions of neurons and trillions of interconnections between them. And what happens is there will be neuro transmitter substances are electrical pulses that each of the neuron emits, and collective information from each of the surrounding neurons will help a particular neuron to take a decision on firing or not firing. Okay, this is essentially the basis for the development of neural networks. So, we will discuss some of these aspects first. Okay, and we start with how the compared to the biological neuron or in motivated by the biological neuron, how a single neuron is mathematically modeled. Okay, we will see the operation of single neuron, and then of course from the mathematical model only, and then we will move on to discussion on the neural networks. Is there any need for neural networks and so on. But the context here, background here is we have we are under the supervised classification setting. We have good number of training samples, okay, and we want to test. We have some test samples to be put into one of the categories. Okay, so fine. Let's start with the understanding of the biological neuron a bit, and then move on to the discussion of mathematical model. Okay. So, I will skip some of the slides. I will come back to the motivation, all those things later. Neural networks are used in several contexts, but we will bring that later. Okay. So, neural networks are not only applicable for classification tasks, they are applicable for regression task in the sense that finding out some variables or real variables of interest. They are also applicable for prediction. That means, if we have some set of samples or if we have a time series and we have the like this values of the time series up to some time instant, and we want to know what happens to the next instance or what will be the values in the next instant, we can still use the neural networks to model them. For example, we know the temperature and few other humidity, etc., few other variables of a day, and we know them for several days. We would like to know it for the next day, for example. We can of course predict it, whether it's correct or not, it will be able to model and predict to some extent. And there are many other applications for which neural networks can be used. We will see them little later. Once we understand neural networks, we will see the applications or the how they can be used in different other contexts. So, as I mentioned, it's motivated by the biological neuron. So, you can see an image of biological neuron here in the slides. So, as you see, there are synapses through which any neurotransmitter substances from other neurons reaches to a neuron, and these are the dendrites which will transmit the neurotransmitter substances like electrical pulses from surrounding neurons to a particular other neuron. So, each of the neuron, as I mentioned, is connected with trillions of other neurons. Of course, we can see that each of the neuron is connected with many other neurons. We can assume that it may be connected to say 10 other neurons or few other neurons, okay, for our mathematical modeling. So, when the neurotransmitter substances gets transmitted to the dendrites, to the synapses of a particular neuron, assume that say we have another neuron here, another neuron here, another neuron here, we have surrounding so 50 neurons or so, which are all transmitting the neurotransmitter substances, and they each of the synapses has a synaptic weight, in the sense that say the inputs given from the surrounding neurons will not be taken equally. Say for example, if we are advised by 10 people, okay, on doing something, okay, whether we do it or not, it depends upon the weight we give to each of these advices. Okay, say for example, if I want to choose IIT Tirupati or somewhere, okay, so then probably we will consult probably 10 or 20 people, and then based on the importance we give or the weight we give to their advices, even though 8 people may say that better not join, but 2 people may say that better join. Okay, so if we give good weight to them, we will be joining here. So it's like that. So each of the synaptic weights decide how much importance to be given to the inputs that they receive from the dendrites of the other neurons, and the weighted sum of all these inputs is what goes to the axon. Axon is the, in some sense, this is the cell body and this is the axon. So axon, this way the firing or not firing of a neuron or decision of a neuron depends upon this weighted sum of the inputs. Okay, and then the action will be taken by this neuron on firing or not firing, or doing or not doing, or any binary classification task. Okay, so now when we come to the our context, okay, so we can we have a mathematical neuron. So I will probably put a mathematical neuron which is easy to draw. So we have several inputs to this. So what are all these inputs now in mathematical to the mathematical neuron? So these are all the features now. Say I have a feature vector of 200 cross 1 as we discussed in the previous example. So I have x1, x2 and so on up to x200 here, or xd. Okay. So we give this as the input to a neuron, and then what I want to say, for example, my objective here is just a binary classification task. I have already a particular, there are only 2 persons, I want to say that whether the face is of this person or that person, okay, or I just want to authenticate, in the sense that say a person when he comes to a lab, I just want to tell that he is can he be allowed or not. Okay, so just whether he belongs to the data set or not, it is a binary decision task. So what I do is I have given a feature vector of a person, I just want to say yes or no here, or I have feature vector, I just want to know whether it is a face or not face. Okay, it is also binary classification task. I have in a bigger image, I have a patch. Okay, is this patch belongs to a face patch or not a face patch. Okay, so I collect the training samples also accordingly. If I have face and non-face classification, I take several patches of faces. Okay, I do take several patches of non-faces. Okay, and then give them as the training samples. Positive class belongs to, say for example, face. Negative class belongs to not a face. Okay. So that you can consider it as a binary classification problem. This is class 1, we denote class 1 by omega 1 and class 2 by omega 2. Okay. So in now these are all in a biological neuron, what we have are the several other neurons are giving input to this particular neuron. Okay, and these are all the synaptic inputs. Okay, these are all the inputs from the other dendrites or synaptic inputs. And as I mentioned, these are all not taken with equal weightage. So how do we take? We take with some specific weight, W1, W2, W and so on, 3 and so on, WD. Okay, so I am just writing in general WD. Fine. So these are all taken like this. After taking all the inputs, weighted inputs, we do have our own bias. Okay, so that bias will come as. We will see what is the need of it in mathematical modeling. But even in biological situation, okay, so there is a bias that is at each of its neuron to fire or not to fire. Okay, because it's already have some preconceived notions or its own bias, okay, a priori interest, okay, firing or not firing, for example, taking a decision or not taking. So summation of all this goes as the output of this, okay. So this is the cell body, and axon is the one which will give the output. So here if I want to take a binary decision, firing or not firing or taking a decision class 1, class 2, see if these are all x1, x2, xd, these are all features, okay, of a particular sample. For example, face image means particular face image is described by x1 to xd, fine. So x1 to xd describes a particular sample or an image or a particular object to be classified to any of the category, fine. So this is the descriptor of the sample, fine. Now this one when we give as input, whether these are all real values, x1 to xd are real values, this w1 to wd are also real values, okay, they are weights. Now what will be the summation of all this, what is the range of the summation of all these things? It can go from minus infinity to infinity ideally, but if I want to take a decision of yes or no or a binary classification, I need not have the range of output being in that wide range. It is good enough, say if I apply, say for example, finally if it is class 1 I can have 1 here, class 2 I can have minus 1 here, okay. So it will easily, it is easy for me to map the outputs in a limited range. So there is one usually a activation function that is used to map this range, real range, finally to 0 to 1 range or minus 1 to 1 range and so on. So this is started with a saturation, but it has very good importance later. This is a nonlinear function which will map this weighted sum to a through nonlinear function, but in a monotonically to the other range. Monotonically means say for example, if this input is higher, the output also will be higher, okay, input is lower, output is lower. So this is a typical example of this f is, you see if I consider this value whatever I have get here as denoted by I denote this by net value, okay. So net is nothing but, in mathematical terms if I want to describe net value, net is nothing but what? So if I have all this as inputs, weighted sum of this itself is the net value. So it is summation wi xi plus b, okay, I ranging from 1 to d, this is the net value, right. And this value I can also write this, I can also rewrite this as what? Can I write in a simple vector can I write with vector notation, sorry, without summation? Yeah, it can be written simply as W transpose x plus b, okay, where W is W1 up to WD and then X is X1 up to XD, fine. Is this fine? Now this f output I consider output as y, okay. So x1 to xd are inputs, y is the output. Y is given by what? Considering this activation function f of net value. Is this fine? Now what is this activation function? As I mentioned, is a nonlinear function. So if I consider f as threshold activation function, how do I describe it is? So it is something like this. So if net value is positive, it is 1. If net value is negative, it is minus 1. That's all. Okay. So this is, I can define in any way. I can consider that f of net greater than 0 being 1, f of net less than 0 being 0 itself. Okay. So or minus 1. So this is how it is defined. So mathematically defining f of net is equal to 1 for net greater than 0. Okay. And then minus 1 for net less than 0. Okay. Is this fine? So yes, this is a thresholding function. This is a thresholding activation function. Why I am using thresholding? Because I say that the weighted sum is what matters. Say the action is binary, finally the decision is binary. Binary decision means just to fire or not fire, okay, take an action or not take, put into class 1 or put into class 2. These are all binary classification problems. Okay. So, in that case, say if the net is towards positive class, okay, one class I consider as positive class, okay, another class is negative class. Net is close to positive class or higher than a threshold of 0, I say it is a positive class, lesser than a threshold of 0, I put it as a negative class, that is all. Okay. This is what is the mathematical model of a neuron. Fine. So, now what is our objective? We started with an objective of classification. Okay, now let us bring in the context here. Assume that we have two features because it is easy to visualize for us. Okay, and then there are some samples of a particular, we are considering binary classification problem. Okay, so let us assume that there are only samples of two different classes. So, we have measured some intensity and then height or width of even faces, face images or the patches. Okay. So, each of the patch we have taken and then just seen the average intensity and then the probably some other quantity variance of that patch or whatever. Okay. So, we have features x1, x2 extracted. So, these inputs are, so how many inputs will be there in that case? Only two features means how many inputs will be there? Only 2. Okay, only 2 will be there, x1, x2. And then weighted sum of that w1, w2 is what essentially we get as the weights there. Okay, now I want to classify them. What do I mean by classifying them? Finally, I am saying that net value greater than 0 is belongs to first class. Okay, net value less than 0 belongs to other class. So, what is essentially this leading to? Say if I write explicitly, so this can be rewritten as what? This can be rewritten as, this is equivalent to what? W transpose x plus b greater than 0 belongs to omega 1, else belongs to omega 2. Okay? X belongs to omega 2. For a particular sample x, okay, for a particular sample x, I have the features x1, x2 for it. Okay, x is this. For a particular sample x or xk, okay, so I can take even xk. So, for xk, for a particular sample xk, if W transpose x plus b is greater than 0, it belongs to omega 1 class, and it is less than 0, it is omega 2 class. Is it fine or not? This is what we are doing finally. Else, or else means what? W transpose xk plus b less than 0 belongs to omega 2 class. Okay, this is what essentially we are doing finally. So, what does this mean? Say in terms of a picturization or in terms of a geometry, what does it mean? We are trying to put a straight line here somewhere, okay, discriminating the class 1 samples and class 2 samples. If I say that there is a straight line here, okay, so there is a straight line here, let us put this itself, okay, this is a straight line, okay, separating the class 1, these are, let this be class 1 samples and this be class 2 samples, okay, so separating the class 1 and class 2 samples. In that case, this is the essentially what is to be learnt or identified by the neuron, that is all, is it not? What is the job of the neuron? See, initially how do I get this straight line directly? Okay, after learning the neuron, after training the neuron, okay, if a neuron is well learnt, distinguishing the class 1 samples and class 2 samples, in such case it will be able to put a straight line like this, is it not? If the neuron is not learnt distinguishing the class 1 and class 2 samples, it will put this straight line somewhere else, is it not? Some class 1 samples will be in class 2 and class 2 samples will be in class 1 and so on, is it not? So, now a learned neuron has the ability of putting like this. So, it essentially is described by what? W transpose x plus b is equal to 0 line, okay, is this, and here what is the for W1, what does it mean by W1? W1 class means W transpose x plus b is greater than 0, and what do we mean by W2 class? it is W transpose, okay, x plus b is less than 0. For what x? For what x? For all the feature points of that particular class, okay, not just for a particular sample, okay. Any sample from class 2 will have this property, okay, if W is properly trained, right, and then any sample of class 1 will have this property, is it not? Okay. So this is fine. So and then the decision boundary, this is referred to as decision boundary. Okay, this is referred to as decision boundary, and this is referred to as whatever we have written here. This is referred to as decision rule. This is decision rule. Okay, fine. So now the question is, how do we arrive at this decision boundary, and decision rule is formed already. Okay, how do we arrive at this decision boundary is the question. Okay. So next question, say for example, what is to be learned here? Say we said that a neuron, okay, has the ability of learning, okay, and it can, once we learn a neuron, any test sample comes, okay, assume that there is a test sample, I have got a test sample, that test sample is somewhere, okay, I just, this is the test sample. To which class will I put it as? W1 class. If a test sample is somewhere like this, then I will put this as W2 class. So once I learn the neuron, okay, with sufficient training samples, okay, and I identify the decision boundary or W's of neuron, then I will be able to put easily classify any test sample. Okay. So now for any number of test samples, the computational complexity will not be as high as we have seen in the nearest neighbor classifier. Fine. But what is to be learnt in a neuron? What is to be learnt in a neuron? Weights. Okay, W1, W2, WD, these are to be learnt. So what are W? What is W? Now the question is, how do we learn this? Okay, we start initially with random weights because we don't have any information. Okay, assume that I started with the W being random, W naught, okay, initialize with random. Okay, initialize randomly, and then we start this process. Okay, but there should be some mechanism to learn the W to classify all the samples of omega 1 and omega 2, class 1 and class 2 to correct labels. Okay. See, now why so if I want to describe this decision boundary by a W, usually what we do is the normal of this is what is W here. So W here is what? What is the line for this particular example? If I consider this as the line x1 minus x2 is equal to 0. This is the decision boundary, assume that. Okay, for that what is W now? If this is the decision boundary, what is W? W is equal to 1, x1 is 1 minus 1, okay, 1 minus 1, right. So this is what is W. So W is represented by, the decision boundary is represented by the normal W, okay. So if I identify, if I have learned this, means finally what I will get? I will only get W1 to WD and B as well, of course, and that is what is my decision boundary. Okay, that will enable me to put here. What is B here? And B here in this example, okay, in this for this decision boundary is 0. Okay. So if I learn for this example, if this is the case, then I will be able to classify them correctly. Okay. So after learning, what I get from here is W and B. Once I get them, I can draw a decision boundary and I can check whether they classify the samples of omega 1 and omega 2 correctly or not. Now is this say for example, I have a sample which is 2 and then half. Okay, so x1 is 2, okay, and then x2 is half. Okay, is this sample correctly classified by our decision rule? Yes or no? So x1 is higher than x2, so it is correctly classified. Okay, so is this sample, say assume that this sample will have just opposite, so half and 2 here and then half here, then is it correctly classified? Yes. See, if I start with assume that I have got this decision boundary, but now there are some samples which are not correctly classified. Okay, I randomly initialize this decision boundary. Okay, but what still I see is there are some samples of class 1 still lying in this side. Okay, and there are some samples of class 2 which are lying in this side. Then what is the problem of learning now? So how do I improve my decision boundary such that I can now have a better decision boundary, such that all the samples of class 1 lie on this side and all the samples of class 2 lie on the, I will put some samples of class 2 here. Okay, so now we want to improve the decision boundary. Okay, so we started with this decision boundary which is not classifying samples of class 1, class 2 correctly, because when we start initially with a random weight initialization, most of the times, okay, all the class 1 samples will not be on the one side and other class 2 samples will not be on the other side. That means we will not get a proper W and B such that this neuron will be able to classify, okay, for all class 1 samples giving y equal to +1 or y equal to -1 for all class 2 samples. It will not happen, it may not happen. In that case, the question is what do we need to learn, or what is the learning procedure we have to come up? We have to have some method by which, okay, we adjust this decision boundary such that all class 1 samples will be on one side, all class 2 samples will be on other side. Okay, for doing that, what do you think is important? Anyway, the procedure of doing it we will discuss in the next class, but for doing that or adjusting the decision boundary or for learning process, what are the samples are of focus for us, or what should we do? We have to see the samples which are, should we see samples only closer? Say there may be some samples even here, okay, which are still farther, but they belongs to the wrong class. All the samples which are not correctly classified, we have to see, okay, those will bring the error. See, if I say that this is classifying all samples correctly, if W transpose x plus b is greater than 0 for omega 1 class sample, there is no error. Okay, but if W transpose x plus b is less than 0 for any of the omega 1 class sample, that will introduce an error. Okay, in terms of this decision boundary correctly classifying the samples. Correct? Similarly, any of the sample of class 2 having W transpose x plus b greater than 0 is misclassified, and that brings in an error. So I have to quantify now mathematically how much is the error in this classification task, okay, given by this initialized W and B. And then what I should do? I should update this W and B, or I should find out better W and B, okay, I should learn for better W and B such that the samples of all class 1, okay, will get lesser error or 0 error, meaning all W transpose x plus b is less than greater than 0 for class 1, and the class 2 samples also get the least error. Okay, so we need to see that for all samples class 1 or class 2 together, class 1 and class 2 together, we should have a less error. So in the next class we will mathematically bring in the cost function or error function, okay, for a given W and B, and then we will try to see how to minimize that cost function with respect to this all samples are misclassified samples, okay, and then find out how to update the W and B, or how to get a learn for better W and B. Okay, that we will see in the next class. On this model of neuron, for a single neuron, the model, initial model was given by several people, but the perceptron model is what we discussed now. This is referred to as perceptron. This is also referred to as perceptron. Thank you. So, we will be discussing some classes on neural networks, and then we will move on to the computer vision. Yeah, sure. Thank you.